Hello, my science lovers. This is an episode of ScientistMel Shorts where I take all of the different topics I had on the science of and compress it down into little bitty bite-sized videos so you don't have to watch an entire live stream that's already been recorded. You can just pick it up from here with the little Cliff Notes version. So let's go ahead and get started. So today I'm going to quickly kind of go through my thermodynamics talk so we can kind of jump into that so you don't have to watch the entire live stream. You can just watch these shorter videos. All right, so thermodynamics shorts. The things that we focus on in regards to studying thermodynamics is the effects it has on a system. This involves work, heat, and energy. First thing we need to understand is that what is a thermodynamic system? It's a quantity of matter of fixed identity and fixed amount. We can draw the boundary around it. Now, boundaries can be fixed or they can move. Work or heat can be transferred across these boundaries. And the surroundings are everything outside of the boundaries. So remember, the system's on the inside. We have a boundary drawn around it. It can either be stuck or we can move those boundaries. And work and heat can move across those boundaries or not. And everything that surrounds those boundaries is the surroundings. What exactly is a system? Well, there are three types. There's open, closed, and isolated. An open system, as you can see with the test tubes at the top here, matter and energy can exchange easily through it. In a closed system, it's got a lid on it. We can't add anything to it or take anything out of it, but we can add heat. We can add energy. Isolated, no heat, no energy. We can't add anything to it. It's completely insulated from all the things. Isolated systems are not terribly common, especially in the biological world, and we'll get into that in just a bit. The Earth is an example of a closed system. Now, matter doesn't really come and go so easily or so readily. Now, not everybody's shooting rockets off in their backyard, and we're not really getting a lot of meteors coming in either. So it's more of an example of a closed system because solar energy comes in and heat leaves as well as light. So that is what we mean by Earth being a closed system. However, living things eat. We exchange matter and energy with our surroundings, thus humans, animals, plants, microorganisms, and the ecosystems they reside in are all examples of open systems. We have energy come and go as well as matter. There are 4 laws of thermodynamics, and you might be thinking zeroth law, what is that about? Well, we're going to talk a bit about that. It's the thermal equilibrium in order, and the zeroth law is important because it's how we calibrate thermometers. The energy is conserved in its form, but it can be converted to various forms of energy. The second law, energies can flow and get to what we call equilibrium. And the third law, as we say, is the driving force for equilibration, and it's very uniquely defined. So we're going to briefly talk about all of those. So what is this zeroth law? So what it means is it's thermodynamic equilibrium and temperature. Essentially, 2 objects are separately in thermodynamic equilibrium. That means they have the same amount of heat transfer as well as temperature, and they're in equilibrium with each other. Now, if we say that object A and B have the same amount of heat transfer and temperature as the thermometer because they are at equilibrium with the thermometer. If the 2 objects, and how do we know that is if the 2 objects were to touch, we can see that the temperature stays the same. This is how we can calibrate thermometers. So if we have 2 objects that have the same heat transfer and the same temperature, the thermometer is going to have the same reading for both. Now you might ask, why is this called the zeroth law? Well, it's called that because it was established after the other laws were established. But they decided people need to know how to calibrate thermometers, otherwise first, second, and third laws are not quite useful because they're heavily based on temperature. So they called it the zeroth law. Now for this one, this is an extension of the conservation of energy. The first law is the conservation of energy and kind of an extension of the conservation of matter as well. Every system in equilibrium that has the same energy and matter in a constant state has an amount of what we call internal energy. That amount of change in internal energy can go up or down, between any two equilibrium states, is equal to how much heat was added to the system and how much work the system put out. So if we look at this equation, delta U, that just means the change in internal energy. It's equal to how much heat is put into a system and how much work is generated out of the system. So you have to subtract that work amount from the heat put in, and that's going to give you that value of change in internal energy. So looking at this a bit closer, each one of these chambers have what we call internal energy. So as we're looking at this graphic, we have heat that enters into each chamber and the pistons move. So that change in internal energy, that change in the chambers, that value is going to be the same as if you take the heat and subtract the amount of work from it. So let's look at this one. This is an example of the ideal gas law, which is PV equals nRT. P is pressure, V is volume, N is the number of molecules, R is a constant, and T is temperature. So the ideal gas law shows the mathematical relationships of matter, pressure, and volume. R is the constant. If I were to increase the amount of molecules, that's the letter N in the equation, and the volume stayed the same, that means that piston didn't go up. The pressure would go up. If I increase the amount of temperature, then kinetic energy would increase and the molecules would be moving around, and this changes the enthalpy. Now, if the volume didn't increase in this case, if I kept the volume constant and I increased the temperature and all those molecules are moving around, now this system could explode. That is why it's unwise to heat up aerosol cans, because the pressure increases due to all of those molecules moving around. Let's look at the second law. Now this comes from NASA. There exists a useful thermodynamic variable called entropy. Entropy ain't what it used to be, right? It's a natural process that starts in one equilibrium state and ends in another, and it will go in the direction that causes entropy of the system plus the environment to increase for an irreversible process and to remain constant for a reversible process. So what does that mean? Entropy increases in irreversible states. Entropy stays the same in reversible states. The change in entropy equals the change in heat over temperature. So that's what that equation is at the bottom. Delta S, that's the change in entropy, is equal to the change in heat divided by the temperature. So let's talk about the difference between reversible and irreversible processes. Here's the second law. Entropy ends up the same. So as the block of ice melts, entropy increases because the amount of disorganization increases. Now, as it comes back together and we cool that water down, comes into a block of ice, entropy decreases because organization increases. That's a reversible process. Now, information entropy is a thing that's actively studied, and we look at it not only in computer technology, but also in DNA. Energy can be spent generating information, and information is organization. So much like putting water back into an organized state, ice, putting nucleic acids together in a highly organized state known as DNA decreases entropy and increases information. Information enthalpy. That's the potential energy with kinetic and internal energy. Evolution does not violate the second law. In fact, it is an example of not only the first law, but the second law. All right, so in regards to the second law, evolution does not violate it. It is a closed system that still does have an increase in entropy. The disorder can occur elsewhere within the system. So just because you're spending energy to generate some kind of information, some organization, that price of entropy still will be paid elsewhere, somewhere throughout the body. 70% of the energy that we intake is released as heat. Nature constantly generates disorder and order. We still lose most energy as heat from our body. So what exactly does all of this mean? Well, let me tell you. In regards to the second law, mutations in DNA do generate disorder. So if we're looking at mutational aspects of DNA, that does generate disorder. But that would only make a substantial impact if we were all in a closed system without any exchange of matter or genetic type of information. That is not the case. Organisms with bad traits tend to not have as many offspring over time to cause a particular trait to stick in the population. If the gene pool stayed the same without any movement of new populations, we would then see an increase in ill traits. Also, this is why we don't have children with family members. That would be a genetically closed system if all you did was have babies with people who likely have mutations, various potentially problematic code to cause it to be pronounced in your closed genetic system. Evolution would eventually cause such organisms to die out and quickly, thus increasing the disorganization and death. This scenario is also making the assumption that no symbiotic relationships would occur. For example, beneficial bacteria to interact and take on some roles, as well as virus interacting with DNA, which in turn could cause changes, possibly beneficial. Evolution does not violate the second law. It follows it to a letter. So now we're going to talk a bit about the third law. Most thermodynamic calculations use only entropy differences. So the 0 point of the entropy scale is often not important. Now, the third law is discussed primarily for purposes of completeness because it describes where 0 entropy can occur. The entropy of a pure crystalline substance is absolute at 0. That means there's no motion, there's no movement, everything is still, and nothing happens. Let's dive into this a little bit further. The third law pretty much states when absolute 0 is reached, how that affects atoms' pressure, volume, and entropy. Essentially, nothing's moving, vibrating, pressure is constant, as is volume. Energy doesn't change, work doesn't happen, nothing's going on. Therefore, entropy is 0. So this kind of just sums up a little bit of what we're talking about in regards to thermodynamics. It's the studies of the effects on a system involving work, heat, and energy. We have 4 laws of thermodynamics: 0th, 1st, 2nd, and 3rd. They all cover different things. The 0th law was important to add because of the fact that we needed it in order to equilibrate our particular thermometers, our thermometers, if you will. So I'm going to take you over to my sources. I know this is a lot of sources, but you can go to my website, ScientistMel.com, and download them all. And they're there for your use. You can use them. You can't read them all here, but download them, take a look, and have a gander at all of the different things that I do here. I'm going to take a moment to thank my patrons: Tony, James, Lauren, Jen, Carl, Melanie, Patrick, Daniel, Paula, Tim, Carrie, Cersei, Keith, Zachary, Tony, Graham, Dragnot, Jennifer, Corey, and Heavy. Thank you for your contributions. If you like what I do, my pledges start at just $1 a month. And if you can't do a monthly thing, buy me a coffee. I do have a paypal.me/ScientistMel. You can check me out there. And I also have gear now from my super awesome artist, Ark, who has stuff that you can get to like have your own gear and carry it around and everything. So, so that ends my particular talk on this. Where can you find me? Everywhere on the internet. Just Google ScientistMel. You can find me there on Patreon, Periscope, YouTube, Facebook, every form of social media. I am also on Instagram. And that thus ends the science of thermodynamics. Woohoo! made it. And this was just crammed into like 15 minutes. So you guys have a super awesome, fabulous day. Ask me your questions in the comments. Hit me up on Twitter and I'll be happy to answer them. Have a wonderful day.